and a good afternoon to all, for the audience. And I'm very honored to be invited to give this talk on the CEPC-SppC status and perspective to the colleagues today attending this seminar. So today I will give the talk on the following subject. I mean the contents. First of all, very briefly about scientific goal, and also describe you the CDR and also the passage from CDR towards TDR, Technical Design Report, and also the R&D status of TDR. Also, I will mention SppC status briefly and the corresponding technologies, R&D, and also I will take time to also to describe some siting and civil engineering. Concerning civil engineering, at the end of this talk, I will give you a video about, say, 4 minutes for you to get a vivid picture of what CEPC is. And also, surely, very importantly, I will mention CEPC-SppC collaborations. Okay, about about physics goal. Since the audience, you are the physicist, and you know very well the importance of the discovery of Higgs in July 2012. It's extremely important discovery in terms of standard model, both within and beyond. So for the first phase of the next step after discovery of Higgs, surely the priority will be a electron-positron collider. We will study Higgs in detail, say, 1 million Higgs in 10 years, and to study carefully of Higgs. And also, if we are fortunate to study, to explore so-called dark matter, all these kind of things. And after that, we will think about a proton-proton collider of 100 TeV scale. So that will be to pushing to the new frontier of energy. So the Chinese scientists proposed the idea of CEPC in September 2012. That means 3 months later. And so the idea is first because low energy of Higgs, so we start with a circular one, since before we're talking about mainly linear collider. So this is the accelerator chain of CEPC in CDR. So that means it has a 5 big system. We have a Linac of 10 GeV and the electron-positron, 1.2 kilometer, and inject into a 100 kilometer booster. Suspended here on the roof, this is the booster. If you can see this arrow. And after it reach Higgs energy, and it will be injected to the collider ring, which on the floor of this tunnel. And on the left of the tunnel, you can see the so-called SppC. In the first phase, this place is just vacant, and only after CEPC experiment, by leaving the machine CEPC aside, we try to put SppC in the same tunnel, which is the tunnel width is 6 meters, which is larger than CERN tunnel diameter, which is 3.5 meter. So that means this CEPC and SppC will be a coexisted machine. And this machine can be later imagined to have EP collision, this kind of things. So that reason why we don't dismount CEPC when we put SppC inside. So this is different from if you compare with FCC at CERN. So this is the journal. Of course, there's detector. We have 2 detectors. Not 4 detectors. So 2 detectors, not 1 detectors like ILC, which is linear collider. So 2 detectors. So about the design, we from the scratch, we say, okay, we want to go to a circle. The most very close machine which has been built was CERN Lab and Lab 2 at CERN, which is single ring with Prism. So we start the pre-CDR design. So what is pre-CDR? So the pre-CDR is the design very quick in 2 years. In fact, just explore the possibilities, but due to the time limitation, this machine, even on paper, it not work. That means it will not reach the luminosity which you need. So this is the reason why it's called pre-CDR. But anyway, we have to work on something to start by study the system and to see. So anyway, in short, we start from a single ring by proposing so-called partial double ring here on the right. So with crab waist collision, the reason why partial double ring, at that time, I think I proposed this partial double ring in 2013 June. So the idea is to have the crab waist collision, but to minimize the cost of the collider. That means only in the colliding region, it's a double ring, but the other part is single ring. But later we changed to, how to say, due to the sawtooth, anyway, the dynamics, the beam dynamics problems, limitation, and beam loading effects. So we moved to so-called advanced partial double ring. That means we have 8 partial double ring, and the rest is single ring. Still, these it's almost touching the design goal, but still it's very difficult to design. And then we finally to put this point of partial double ring until you see the on your right below this picture, until the RF. So that means all these half ring, almost half ring, are double ring, but only the ring go through the RF is single ring. So that means this is the reason why it's called full partial double ring. It's not a total double ring. A total double ring is like a separate KKB, KKB, or BPC, BPC2, this kind of thing, or PEP2. this kind of thing, which is really double ring with two independent RF, both for electron and positron. So I have to be quick. But finally, this so-called full power double ring was chosen to be our baseline design. So this is the baseline design I've shown before. And you see Higgs, this machine is a full power double ring, but about when the machine work on W and Z, we switch, not changing the hardware by just changing the beam passage, we switch to W and Z mode. So this is different from FCC. FCC is the RF system is different from WZ and H. And the TT bar also. So okay, so this is the parameter, CDR parameter. So the luminosity are about per IP is about the 3, 10 to 34, and for the Z is 32. Anyway, I'm not going to the detail. So this is the CDR parameter, and then we finish CDR in November 2018 and publicly released, which is earlier than the FCC CDR, which was released in the beginning of 2019. And also, we actively participate to the European strategy, and we submitted the 2 documents. One is Accelerator, another is Physics Detector, both about 10 pages. And after that, we continue to optimize the performance. That means luminosity by reducing the beta Y, and for the Z, so for the Higgs, and then it's another thing, we be careful if you compare with FCC Higgs, is that we use 30 megawatt instead of 50 megawatt. Surely you can use 50 megawatt to have higher luminosity. However, your AC power will be proportionally high. That means around 500 megawatt. So we make, we choose, say, 300 megawatts. So that means this machine not surprise the government too much by consuming power, at least for the, you know, linear collider consume 100, say, 30 or 40, anyway, it's around 100, less than 200 megawatt. So this is the difference I just show you. This is 30 megawatt radiation power per beam. So FCC is 50. And about the Z, so we change to, we make a new design of single cell, and instead of 2 cell for Z, and then we can reach 100, 10 to 34 luminosity. CERN is 200 with 50 megawatt. Anyway, so this is our philosophy and the design, so which is maybe from one lab and one group of designers. There's some difference, but in general, they are not very different. Anyway, it's 200 or 100, 10 to 34. Okay, so this is the accelerator design. I will not go into detail, but the most important thing is the dynamic aperture. That means the opening of the stable area not the hard boundary of vacuum chamber, but the dynamic aperture for the beam to be stably stored in the ring. So this is important because if you have the reason why we have pre-CDR doesn't work because CDR, pre-CDR, we have zero dynamic aperture. So it's very difficult. That means corresponding to what? Corresponding to your designed luminosity goal. If you put your design luminosity goal to the lab or lab 2, single ring, it works. Okay, so you can see that the aperture, the higher the luminosity, the smaller the beta Y, the strong the nonlinear effects, and the smaller dynamic aperture. So that is the reason why we have a minimum design goal of 2×10⁻34 luminosity for Higgs. So that means if you reach that, if you use single ring, you have zero dynamic aperture. So this is in the domain of accelerator design, the language and the parameter which we this is due to chaotic motion in a nonlinear periodic system. So this is RF system. So you see this kind of arrangement I have explained before. So I will not go into the detail of this because I don't have many time. And so this design is different from CERN. CERN don't have this kind of design because they will change from one energy to another. They will stop the machine and change the hardware. And so in the CEPC design, we don't want to change hardware. We just want to change the switch from one energy to another, just like a CEPC BPC2 right now in Beijing in IHAP. You change the energy, but you don't change hardware. So the frequency of RF, we have two frequencies. One is in the booster, another is collider ring. The collider ring, the frequency is 350 megahertz. We need many cavities, let's say, in the order of 200 cavities, 2 cell. But for the booster later, I will show maybe, so anyway, I mentioned here for the booster, the frequency is 1.3 gigahertz, 9 cell, which is, the crown module is 12 meter long, so which is almost same as linear collider. The only difference is the field is not so high like linear collider, but we need a high Q. So this is the MDI layout. So we, as I said, we have two detectors, and the L star is 2.2 meter, and the angle, crossing angle is 33 milliradian. So if you measure the distance between at the entrance, that means L star, 2.2 meter, the separation of the beam pipe is about 6.6 centimeter. So which is in the same number or the same order of magnitude of difference separation like Super K. Super K has a shorter, much shorter L star, but much bigger angle. The separation space is almost same. So this is determined by your technology, superconducting magnets. So this is the booster. As I said, the energy of Linac is 10 GeV. You have to increase your Linac 10 GeV from 10 GeV to 120. So for the booster, the main challenge is you can imagine, because this is a huge ring, 100 kilometer. So the dipole magnet field is very low at 10 GeV. That means injection energy. So the dipole field and the injection energy is only 28 Gauss. So compared with the field the Earth field, which is less than one Gauss. So this is a very low field. And you need this dipole ramp from low field to high field, and then back to very low field. So these kind of magnets is very difficult to design, and because there is no dipole, a real machine with a dipole field so low. Because if you see all the light source collider or a circular machine and the dipole magnets field is higher than 100 Gauss, several 300 or something like that, and never 30 Gauss. So this is very challenging. Of course, you can say that we can increase the injection energy from 10 GeV to 20 GeV to 30 GeV, increase the field by a factor of 2 or 3. But you can imagine that due to the increasing the injection Linac, the length, the cost also will increase. So we first fix injection energy of 10 GeV. What about the 10 GeV machine like? If you look at the Korean XFEL in Pohang, which is exactly 10 GeV Linac, so which is about 1.2 kilometer, more than 1 kilometer. Okay, so this is a machine like that. The frequency, okay, I will not go into the details. So this is the lattice of booster. And about the cryogenic system, because booster and collider ring cavities are working at 2K. So we need 4 big cryogenic plants, each 18 kilowatt at 4K. So so this is a big cryo plant. It's a plan. Till now, this kind of thing can only be built by 2 companies. One is Linde and another is Air Liquide in France. So we are working on this. I will show you later maybe. About polarization, you know well that lab has made in the 90s polarization in lab. So anyway, so you know, linear collider can make polarization, say 80% or something like that. Anyway, to gain the physics experiment precision and also the possibility to make more flexible. I mean, so for the circular, it's very difficult because it's easy and difficult. It's easy means you can self-polarize your beam, but it will depolarize also. So to make to use a polarized, self-polarized beam to calibrate energy, we use only 5 to 10% of self-polarized beam, vertically polarized, and these can be done by introducing very special undulator in the collider ring without injection of polarized beam, but your beam will self-polarized by these wigglers, special wigglers, and then this is the parameters, and then the check of polarization, and also then aperture. However, if you want to use polarization longitudinal with a high rate of polarization to make physics experiments, surely it's more difficult. You have to work not only on collider ring to make the polarization to rotate from vertical polarization to the longitudinal direction in IP, And also, you have to inject a polarized beam right from Linac to booster and to the collider ring. So this is a so-called injected polarized. But imagine we have a polarized injector, Linac. And if you inject the 10 GeV polarized beam into the booster and increase energy from 10 to 100, 120, the polarization will be destroyed. But you can use the so-called Siberian snake, these very special magnets, to avoid the crossing, the so-called very special resonance to destroy your polarization. So this kind of thing has been studied, and so-called the Siberian snake in the booster. And surely this polarized beam is very complicated. And in fact, this is not a charge, very fundamental charge for the accelerator designer. However, we are exploring the possibilities. You will ask also, how about the whether at Higgs energy you can have polarization in the ring? So the answer is no, because with energy increasing, the depolarization time extremely short, and you have almost no way to maintain polarization in the high energy like Higgs. How about the W? Maybe boundary, maybe not. But anyway, one thing is sure is at Z energy, 45, it's possible. So this is something, a picture for you to understand the polarization. So this is very academic, and students or some people, limited number of people are working on this. We are coming down to Linac, from collider ring to booster and to the injection Linac. Linac is very conventional. This is S-band. And if you look at this, is very similar to Super K Linac with a damping ring, which is for positron. Because you produce in the target the positron, but the emittance is very big, and then you need to shrink the size. So for this positron, so you need the damping ring for the positron, which is here. It's a circle in the middle of the Linac, and then so this is the damping ring. Physically, it's like that. 1.1 GeV. So, as I said, the injection energy is very low, 10 GeV. So we had an idea which started in the beginning of 2017 in a travel to AFAD meeting in Lanzhou. I think 2 years before, the AFAD meeting was in New Delhi. So this is the previous AFAD meeting in Lanzhou, and we had this idea to say, why not we use a plasma accelerator just after this 10 GeV Linac to boost the energy of electron and the positron from 10 GeV at least to 45. So that means you increase energy by factor of 3. In this case, your dipole field can increase by a factor of 3. So so one day, if you can boost from your Linac the energy from 10 GeV to 120 directly injected into the collider ring, avoiding using booster. Of course, it's great, but the gap is too big. It's for the moment, we don't think this is is easy in the for coming years. But 45 GeV by of boosting the electron beam from Linac is possible. And also the properties of these plasma produced high energy beam can satisfy the requirement of your booster. Imagine we have a bigger stoma to say we will use this plasma accelerator to make a linear collider to have luminosity. Personally, I believe in the next, say, 50 years, this dream can be realized by cascading a plasma accelerator just after ILC to boost your ILC from 1 TeV to 10 TeV, for example. But that will be a passage, I mean, in the next 30 or 50 years. Maybe quicker, maybe longer, because you want to have a luminosity at the same time, in addition to energy. So this is something new, and we are working on this simulation, and I did not show you too much, but on paper it works. And for the moment, we are making the experiment in Shanghai XFEL, soft XFEL Linac. And also we make 2 proposals to Facet 2 in Slack and to demonstrate positron acceleration, which was the goal, the aim of Facet 2 also at Slack. So this is the quadruples, and so I will not go into the detail of this for the MDI part. Anyway, we use superconducting magnets to squeeze the beam, the beta Y, to 1 millimeter or even sub-millimeter later. Imagine if you look at super K, the design goal of beta Y is 0.6. I mean, even less than 0.6 maybe, but anyway, it's sub-millimeter. Okay, so this is the interaction region, the beam pipe, because this is the key place connected with detector. You don't want big noise background due to either from Baba scattering or from synchrotron radiation upstreams and also beam gas interaction. Anyway, you don't want. Also, this beam pipe is very small size, and also due to the wake field and the high order mode and with high current, especially at the Z mode, the temperature will increase. So you need to cool them and not to affecting your detector around. So this is the detector, which is not the main content of my talk, but I just to show you what was in the CDR. And also there's an Italian group proposed the so-called idea concept. And mostly the CDR CEPC detector is very linear collider like, but also we're working on the silicon detector, technology. So now we are going to the, so 30 minutes passed. So I will, talking about R&D in the TDR phase. TDR is technical design report. Um, so that means we have already CDR. What the definition of CDR? CDR, different from pre-CDR, is this machine on CDR can work at least on paper. That means it reach your design goal only on paper. So before the construction of the machine, you have to demonstrate your technology will be at hand and you are ready to put to construction, to industrialization and fabrication, installation and operation. So these things, we define this work just like is technical design reports contents. So here I list some accelerator related R&D priorities, not complete, but just to give you some idea, and I will show you later the concrete progress. The high efficiency klystron. Why high efficiency? As I said, a circular machine, different from linear collider, is its needs more AC power because of the synchrotron radiation. Linear collider, you don't have that, so it's power consuming, saving. So we have to increase the klystron efficiency. Klystron is the component to transform from AC power to the RF power. And from RF power, you can put it into the beam power. So the efficiency need to be increased. We have a goal of 80%. The commercial klystron now, right now, in different frequency range, very standard is 60%, 65. So we're trying to make 80%. Because 80% compared with 65%, it's a big amount of AC power reduction. And also here is the high precision booster dipole. That means imagine we don't increase 10 GeV, we need to make these dipole magnets very precise. So difficult, but we need R&D. I will show you later. And also the cavities. We have two kinds of cavities, one for booster, another for collider. One for 1.3 gigahertz, another 350 megahertz. We need the high field, also high Q, very high Q, just to save energy. Also, dual aperture, because the beam pipe is two, electron and positron. They are moving in different directions, but the magnets, we use single magnets, dipole and quadrupole, as a single piece physically, but with a two aperture. So we need to make these kind of dual aperture magnets. And also vacuum chamber. So we have to coating and high vacuum and also. And superconducting magnets, MDI, mechanical system, installation and beam pipe connection and all these things, very many complicated system. Collimator, Linac component, civil engineering, plasma injector, and the cryo plant. This is in collaboration with company. Of course, there are others, but I'm not listed everything. About this detector R&D, so I listed here something you can read. The silicon vertex detector and also muon detector and also all these things, which is so all these things has to be studied in, but in this phase, only accelerator in the TDR phase, but not detector, because as you know, detector usually the phase to making a detector is a little bit late compared with accelerator, because always we want to use the most advanced technology in the detector design. So the detector design usually a phase slower than the accelerator, just like IOC. So this is the CEPC superconducting R&D progress. You see, this is a test model. I mean, a test model. In fact, the real one is 6 cavities, much longer than this. So we are working on these cavities, and also we study high gradient cavities by using large grain, single cell, and we're working on the 9 cell cavities for a long time, because we have been in collaboration with IOC since 2005. And so this is the cavity R&D progress. I will not say too much about this. Also the components, couplers. This is important because we are working on a new superconducting lab, which is 4,500 square meter, 1.5 hour drive from IHAB in Beijing, but in suburb. And so this lab will be ready for the assembly cryo module and testing, vertical test of cavities, and also with cryo module with beam. All these things can be done in this new lab. This new lab will be finished in next year. So this is the klystron. So you see the klystron is, we have 3 phases of doing that. Right now, we just completed the first phase. That means the first 350 megahertz klystron of efficiency 65. And in the experiment, we reached 62%. And also the power, we reached the design goal. So in this study, so we test our simulation, or mechanical, I mean, design and mechanical fabrication, the welding, and also transportation from Shanghai to Beijing, and long distance, and also high power test. The next step, we will have 2 steps following this. One is a high voltage from 90 kilowatt to 110 kilowatt, single beam. And the next one will be multi beam klystron. The efficiency will be a little bit more than design one, 80%. So so the next 2 klystron is under design, and hopefully next year we'll finish the second, and after that we'll finish the multi-beam high efficiency klystron. So this is physically the klystron it looks like here. It's very long, and this so this is the multi-beam klystron. So all here we are talking about the collider and the booster ring magnets. So this is the design, and we make a model test. For example, this is the dipole, and so here is the real one. We want to build a real one of almost 6 meters long. Mechanically, it's very difficult. We hope can finish this piece, but this is already finished, short one, 1 meter long. So low field booster dipole, we have two. This is specification. We have two designs. One is with iron core. Another is without iron core. Just so for the moment, the difference is this is the with iron core you save AC power. You need lower current, lower power consumption, but with this air core, you need more current and more AC power. But surely air core have is more precise with when you ramp your field. It can goes up and goes down to the field to the position you start with. So till now, these air core dipole has been satisfied the design goal, but the iron core dipole not yet, with a factor of 2 or 3 difference with the design goal. So this is the electro-magnet separator. Why this component? Because as I said, in the main part of the ring, it's 2 beam pipe. And in the RF region, it becomes 2, it's combined into single beam pipe. And the RF for Higgs is used both for electron and for positron. So that means your bunch train is filled only half ring, not a whole ring. If you have a real double ring, you can fill your bunch train independently in the full ring of your storage ring. So this vacuum chamber of 6 meters long, aluminum and copper. One for aluminum, another for one for electron, another for positron. Also, we have to coat this neg coating on the, to reduce this secondary electron emission. So these superconducting magnets, this is final QD0, QD0, QD1. Because the separation is very small. As I said, it's only at the entrance only 6.6 centimeter. Sorry, it's not easy to design this. So we are working on that. For example, we are working on the for the cooling, the how to say the coil hardening system, and also the winding machine of superconducting magnets. So this is the detector MDI issue. So this center is the beryllium pipe. And because so the beryllium pipe and also the superconducting beam pipe has to be connected in vacuum, but this connection is inside the detector. You cannot use your hands to fasten the bolt. So we have to use a system of different system. We have 3 designs to have a so-called remote connection to make a vacuum beam pipe connected. One is very similar to CEPC, and another 2 is different. So we are working on this. So this is the process how to assemble your beam pipe together with the detector. So this collimator, you have to collimate the how to say the gamma ray from upstream and to avoid the background in the detector. So this is the Linac technology. This is the energy doubler circle one, not like a slack one. And also the new Linac S-band with higher field, say more than 30 megawatt per meter. And this is for the positron source, this flux concentrator and the power source. Okay, so this is cryogenic plant study. And you see this year, we can finish, not this is industry. They can, this year or next year, they can have, say, for the moment, the industry level, I mean, technology level is about 2,500 watt at 4K. This is already quite big, but compared with what we need, 18,000 watt. So there's still a gap. So we hope in the next 2 or 3 years, we can have the industry can fabricate this big refrigerator. About laser plasma acceleration and the experiment, you see the setup has been established in Shanghai, and also other small experiment, technical, I mean, physics proof has been conducted in Tsinghua University. So SppC status. So this is the parameter, and the baseline is 100 kilometer, and the magnet field level, we choose 12 Tesla as a baseline. Why 12, not 16 like CERN FCC? So we thought 12 is something this connected with the technology which we propose, so-called ion-based superconductor, not niobium-13, which is commonly used in accelerator, but very expensive. So we, since SppC is not imminent, it will be after CEPC operation. So we still have time to make R&D. So we choose a very promising so-called technology road to use a high ion-based technology, high temperature also. So the luminosity is 10 to 35, and the energy with 12 Tesla is 75. If we can increase, say, to 20 Tesla, and this machine can reach 125 TeV. So, so the layout of SppC is more complicated because you need the injector chain. Because CEPC-SppC is different from CERN is that this machine is in the green field. So CEPC is relatively simple, but SppC is more complicated. You need a injector chain, a 3-ring. And also another thing, the complication is these two machines are not independent. They depend each other because they have to in the same tunnel with the constant distance, and also in the interaction region. This beam the two machines has to to bypass the detector region of the other. So it's a complicated. Um, so this is the subject, very special subject we have to tackle, but not FCC. So about the progress of high field dipole magnets. So there's some progress, and for example, we reached this 10 Tesla to 4K with this material, and with diameter of this, which is small. Of course, we want to increase this. This diameter surely is not only for test to reduce the cost, and to, but in the real magnets, this phi it's bigger, say 40 millimeter. Anyway, so this kind of work is progressing, and so about the ion-based superconductor, there is a very, how to say, good news, and the experiment shows that this is a good direction, and we need just to go forward. We hope in 15 years, the cost of ion-based dipoles can be reduced by a factor of 10, and the field level, I mean the JC, the current density, or the field can increase, I mean field, the JC can increase by a factor of 10. Anyway, this is based on this judgment. We think SppC can be built. Otherwise, it's if based on so-called Nalbin 13, the machine will be very, very expensive, as you can see in the FCC cost. It's very high price. So we are in close collaboration these years, not this year, but recent years with CERN, working on high luminosity, electricity steering coil, this magnet.
Just one thing. Just wanted to check how long do you think will continue?
I will, I think, so how long I have already, 1.5 hours already, right?
1 hour, 1 hour is complete. So
I will within, I think I will be quick, and within say 10 minutes.
Okay, maybe a bit less than that would be better.
Okay.
If okay.
Understand.
Yeah.
Understand. So sorry, I am too slow. So I will be quick. So this is the magnets we deliver to CERN. Okay, so this is the civil engineering. This is siting, and there are 6 sites. In the north side, we not yet decided. This is civil engineering. This is the beam numerical design. I will show you later. So this is the tunnel facility, IR region, and the power. We need, you see, for Higgs, we need almost 300 megawatt. So about the time schedule is, we hope we can from 2023 to 30. So this is, of course, this is very, how to say, ideal plan. International collaboration we have with industry, CEPC, and also we have international advisory committee, and also we have many meetings in Hong Kong, in Rome, in Italy, and in UK, and also in the US, Chicago, and this year in Marseille, but due to this virus, so we just moved to next year. So this international advisory committee member for the Accelerator, And for the detector, we have two groups of reviewing committee, standing committee. So this is summary. I will not read this one. So thank you very much. And I will show very briefly a video.
The CEPC is a large international scientific project initiated and will be
Jay,
hosted by
it's
China.
not
Yes.
coming.
As a crucial
It's not showing
cornerstone
up.
of the standard model, Higgs boson is at the center of the greatest
Just a
mysteries
moment.
of modern.
Sorry?
We can hear it, but we can't see it right now.
You can't see it?
Yeah.
Oh, you can't see. But before you saw it, right?
Yeah. So
Maybe I again I stop sharing and then I share again
sure.
the screen. I share. It's
The
okay.
CEPC is a large international scientific project.
Now it's okay.
No, I think it disappears when you.
Of the standard model.
Yeah, this is fine
Higgs
actually.
boson is at the center of the greatest mysteries of modern particle physics. Precise measurements of the properties of Higgs boson serve as excellent tests of the underlying fundamental physics principles of the standard model, and they are instrumental in explorations beyond the standard model. In September 2012, Chinese scientists proposed the 240 GeV circular electron-positron collider for Higgs studies. The CEPC Accelerator is a double-ring electron-positron collider located in 100 kilometer circumference underground tunnel. The huge machine consists of a linear accelerator called Linac, a damping ring, the booster, the collider, and several transfer lines. Besides, two large detectors rolled in. The interaction points will collect data of events produced by the collider in the tunnel. Enough space is reserved for the future proton-proton collider. The Linac is at the ground level with a length of 1.2 kilometers.
This is an electron source. This is the positron target. And this is the damping ring.
There is a damping ring to squeeze the positron beam evidence.
So now from the surface to underground, both electron and
The
positron.
Linac and the booster are connected by two transfer lines for electron and positron beam, respectively. The booster is underground at a depth of approximately 100 meters. There are 8 straight sections in the collider, 2 interaction regions, 2 RF regions, and 4 injection regions.
So this is the RF for booster. This is the RF for the collider. This is the Electron.
Electron and positron beams circulate in opposite directions in separated beam pipes. They collide at two interaction points. The CEPC is an important part of the world plan for high-energy physics study. It will support a comprehensive research program proposed by scientists from all over the world. Physicists from many countries will work together to explore the science and technology frontiers and to open a new era of our understanding to the fundamental nature of matter, energy, and the universe.
Okay, so thank you very much, and sorry for a little bit long.
Okay, thank you. I'll open the floor for questions. Please go ahead.
Rishi, I'm Govinda. Can you hear me?
Yes.
Yes.
Yeah. I have two very small question about your early part. First of all, why we need two tunnel? Let's say left had only one tunnel and they're both electron and positron in the same beam pipe. Here you are having the two tunnel for electron and two beam pipe for electron and positron.
Yes.
So why?
So this is exactly in the beginning I explained. So in the beginning,
Sorry, I might have missed it. Yeah.
Yeah, it's okay. In the beginning we use a single ring, like a lap, to reduce the cost. However, if you want to increase the energy, the luminosity from lap to CEPC, the luminosity is in the order of 1,000, more than 100, surely. So you need more bunches, and due to the synchrotron radiation, the energy in the two directions of beam is different,
Okay.
going into one magnets. This is so-called the sawtooth effect. So to correct these, and also you have to separate, because you have a single ring, you need more bunches, say 50 bunches. You need the so-called Piezo scheme to separate them in the parasitic crossing point. So all these things, gymnastic, makes your luminosity almost unreachable to the design goal. So that reason why we have to adopt this independent beam pipe.
Okay. Sorry, another small question. You said that we do not have very low field dipole. So why what is this major problem to have this low field dipole magnet?
Yeah, so you know the low field is the working field is 228 is 28 Gauss, and the street field, I mean the street field and the earth field in the tunnel is in the order of around 1 Gauss. Some place in the real machine tunnel is 2 Gauss. If in a real machine, in the in the space outside, maybe 0.5 Gauss. Anyway, so the working field with the residue field is very low. This is one thing. Another thing is you increase your field, and then you goes down to the origin point. So the spread of this point, the spread, this and this field spread compared your working field. So it's quite big.
Okay.
So all this makes you this booster cannot work if the precision of booster is not well designed.
Okay, understood. Thanks a lot.
Okay,
Yeah.
and Kajri has a question. Yes, Kajri, you can go ahead.
Okay, so can you please go to the table towards the beginning again, maybe slide number 8, 9 or somewhere, where you are comparing towards the beginning. I don't remember now. Yeah, maybe 8, 9, where you had shown what is happening with the luminosity, and there was a table.
Luminosity table.
Luminosity and the number here. So the last one, if we can see, it's not very big actually. I'm not able to see. So you said Z 3 Tesla versus Z 2 Tesla. So
Yeah.
what is happening with 3 Tesla? You are getting less luminosity. I'm not able to see the number. Is it 16 versus 32 or
16 for 3
versus
Tesla.
32?
Yeah.
Why it is
And,
so?
This is due to
2 Tesla
the,
means you are squeezing the beam more, or what exactly this means? Z 3
2
Tesla Z
is the detector magnetic field.
detector magnet. Okay, fine. So
And
with 3 Tesla, are you missing or what exactly is it?
so the higher the field,
Yeah.
the higher the detector solenoid field, the bigger the coupling of the electron or positron beam in the XY motion.
Oh,
So,
okay.
so this is due to the emittance will blow up. I mean, due to coupling, and that reason why the lower field is better.
Okay, thank you. Okay, I was
From X-ray side, of course.